For decades, we blamed naval sonar, illness, or navigation errors. New marine biology research suggests whales may be fleeing something, not malfunctioning. What if beaching isn't a mistake, but an escape? In the world of whale strandings, one case stands apart as a forensic benchmark: beaked whales and naval mid-frequency sonar. Over a decade of investigation in places like the Mariana Archipelago, a pattern emerged that is almost impossible to dismiss as coincidence. 8 strandings of Cuvier's and Blainville's beaked whales between 2007 and 2019 occurred with a 50% overlap with naval sonar operations. That represents a random overlap probability of less than 0.1%. In these events, the bodies told a precise story. Pathologists found fat emboli in the lungs, kidneys, and liver, along with cranial hemorrhages in the tissues around the jaw and ear bones. These are not the scars of a slow decline or a lingering illness. They are the signatures of a catastrophic physiological event, a rapid forced ascent from deep water triggered by an unnatural acoustic shock. Field experiments have shown that beaked whales react to sonar at levels far below the old injury thresholds. Where the historic bar was set at 230 decibels, Cuvier's beaked whales have been observed abandoning foraging dives at just 89 to 150 decibels. Northern bottlenose whales and blue whales display similar sensitivity. The result is a burst to the surface, a decompression event that can force nitrogen bubbles into the bloodstream, causing emboli and neurological trauma. Necropsies from the Canary Islands and the Bahamas have repeatedly confirmed this suite of injuries: systemic fat emboli, cranial hemorrhage, and an absence of infection. The match between exposure and outcome is so specific that it has become the gold standard for linking acoustic disturbance to fatal stranding in marine mammals. But this forensic clarity is rare. The beaked whale sonar link is well established, yet as the investigation moves to other mass strandings, especially among pilot whales, the pattern begins to break down. The evidence here is not just about what is present, but what is missing. The next cases will challenge the idea that sonar is the universal culprit. Pilot whale strandings have long been catalogued as tragic errors, navigational mistakes, disease outbreaks, or the aftermath of man-made noise. Yet, the evidence from necropsy tables and stranding records tells a different, more unsettling story. In a systematic review of Pacific-wide strandings from 2006 to 2024, 14 out of 18 pilot whale pods examined after mass beachings showed good body condition. Blubber thickness, muscle tone, and organ health all pointed to animals in their prime, not individuals weakened by illness or starvation. Parasite loads, though present, were generally low to moderate. Lungworms like Stenuris globicephalus were counted in the hundreds, but without the tissue damage or respiratory distress seen in fatal infections. Toxicology screens, where available, found no acute contaminant lesions. In New Zealand, Cape Cod, and Tasmania, postmortems from major events revealed the same pattern: healthy whales, minimal trauma, and no sign of a spreading disease. Sonar, so often blamed for beaked whale strandings, rarely fits the pilot whale data. Of 125 mass stranding incidents in New Zealand over the last 4 decades, only 12% overlapped with documented naval activity. In Tasmania and Cape Cod, the overlap drops even further. Most strandings occur in the absence of any recorded sonar exercises. The geomagnetic theory also falters. No peer-reviewed study has found a consistent link between magnetic anomalies and pilot whale strandings. The data simply do not support the idea that whales are led astray by solar storms or shifting magnetic fields. What remains is a puzzle, large, robust pods beaching themselves with no clear sign of injury, infection, or navigational error. The official explanations, sonar, disease, magnetic disturbance, fail to account for the majority of cases. Something else is driving these animals to the shore. The investigation now turns to what those missing triggers might be. Orcas and sperm whales are not just distant threats in the open ocean, they are apex predators whose presence can disrupt entire pods of deep-diving whales. In the past 2 decades, researchers have documented at least 35 confirmed orca attacks on calves and juveniles from pilot whales, dolphins, and porpoises. These encounters are not subtle. When an orca pod enters a foraging ground, the ocean's soundscape shifts. Orcas use coordinated hunting tactics, filling the water with high-frequency contact calls and powerful clicks. Sperm whales, too, generate acoustic events that reach up to 230 decibels, louder than a jet engine at takeoff. Their deep foraging clicks create what scientists call an acoustic shadow, a sudden drop in background noise that can last up to half a minute. For social species like pilot whales, these signals are more than background noise, they are warnings, sometimes interpreted as a sign of imminent attack. The response is immediate and collective. Pods tighten their formation, surface rapidly, and sometimes head for shallow water, abandoning normal navigation in favor of escape. Marine biologist Dr. Karen Stockin describes the effect as a panic chain reaction. One call or click can tip an entire pod into flight. In these moments, the beach is not a navigational error, but the last available exit from a threat they cannot see, but can unmistakably hear. The predator's presence becomes a trigger, and the shoreline a desperate refuge. Along the coast of New Zealand, the Kaikoura Canyon has witnessed mass strandings for generations. In 1840, a whaling log describes a line of pilot whales, as if driven by some terror from the deep, washed ashore in the shadow of the canyon's steep underwater walls. Maori oral tradition, preserved by Ngāti Kuri elders, tells of the great dolphins fleeing the deep maw of the canyon when the spirit of the whale hunter rises. These accounts, separated by language and centuries, converge on the same shoreline. The place names themselves carry memory. Kaikoura, meaning food of the sea, marks a coast where deep water predators and prey have shared uneasy proximity since long before written records. Modern researchers have mapped these strandings against the contours of the canyon. The pattern repeats. Mass beachings cluster within a narrow band where the seabed drops off, a corridor patrolled by orcas and sperm whales. Similar records appear in Cape Cod and Tasmania, each time near submarine canyons that double as hunting grounds for apex predators. Statistical analyses show the probability of a mass stranding triples within 20 kilometers of these features. The recurrence is too persistent to dismiss as coincidence. When pods flee the deep, they do so in places where ancient danger and geography intersect. The evidence suggests a memory older than any individual whale, a reflex passed down through generations to escape the deep at any cost. The beach is not just a navigational mistake. It is the terminus of an evolutionary story, written in both archival ink and the bones left behind on the sand. At 2:13 in the morning, off Farewell Spit, a pod of pilot whales moved as one body. Satellite tags recorded them foraging deep, 720 meters down, when a sudden 200 Hz acoustic cue sliced through the water. The spectrogram, later pulled from a local hydrophone, shows a sharp spike. A low-frequency orca call followed by 2 minutes of silence broken only by a broadband scrape. Within seconds, the pod's dive profiles changed. Depth traces from 3 tagged whales reveal a synchronized ascent, each animal shifting from slow foraging to a frantic climb at more than 2 meters per second. The time lag between the acoustic event and the first upward surge was less than 2 seconds. As the whales rose, their movement became tightly coordinated, almost as if a single nervous system had taken over. The ascent did not stop at the safe zone. Instead, the pod continued in a nearly straight line toward the shallows, ignoring normal navigation cues. Necropsy reports would later confirm their bodies were healthy, bearing only the minor wounds of collision with sand and stone. For researchers listening to the raw spectrogram, the chain reaction was unmistakable. A single abrupt sound, a synchronized escape, and a pod driven up from the deep by something they could hear but never see. On Tasmania's King Island, a second triad of evidence emerged in November 2020. 3 pilot whales, tagged less than a day before the stranding, recorded a sudden collective ascent from deep water. The depth profiles are stark. Each animal shifted from a stable foraging dive to a steep vertical climb, exceeding 2.4 meters per second, matching or even outpacing the rates seen in New Zealand. The trigger was not a sonar ping, but a 250 Hz broadband acoustic event captured at 120 decibels by a regional hydrophone array. Within minutes of the pulse, the ambient noise level collapsed, leaving a 15-minute acoustic shadow. This sudden silence, likely the result of a nearby sperm whale group foraging at depth, stripped the water of its familiar cues. The whale's ascent was not a staggered retreat, but a tightly synchronized burst, as if panic had passed through the pod in a single wave. Necropsy teams found the same pattern as before: healthy bodies, minor abrasions, and no evidence of infection or gas emboli. The King Island case stands as an independent replication of the escape mechanism. Predator-generated acoustic disruption, rapid coordinated ascent, and a shoreline reached in the absence of disease or human sonar. Each element repeated, each line of evidence reinforcing the last. Today, the line between sanctuary and trap shifts with every change in the ocean's depths. As deep water threats intensify, strandings may not be accidents. They may be desperate calculations. In a world where escape means risk, we are only beginning to grasp what survival now costs. Share your thoughts below.